Hello, everybody. We're going to start talking about something new today. It's going to be a one lecture wonder, and it's going to be pretty complicated. So complicated that it's unlikely that I'll test you very heavily on this topic at all. I'm going to be introducing the concept of PDEs to you. That's going to be new to just about everybody in the class. It's partial differential equations. It's a step beyond differential equations. And as such, because the solution methods are really complicated, I'm unlikely to touch on this on a final exam in anything more than a basic way, okay? That being said, I want you to know that I'm doing this for a reason. I'm doing this because it's important. There are a lot of later courses in a variety of different disciplines, math included, where these things are going to arise. And where they're going to arise, sometimes their actual, finding solutions to these partial differential equations can be extraordinarily difficult or oftentimes impossible. So what we want to do is approximate those solutions numerically. And we're going to cover a basic scheme here to kind of help you understand which way is up. If there's anything you get from this lecture, if there's a little bit of understanding of what PDEs are, if there's a little bit of an extension on I understand this method because I understand how Euler's method worked a couple of weeks ago. Awesome. If you get stuff from this, that's what's important. But why don't we get into it? And we'll see for ourselves. I want to do a bit of a careful job talking about what a PDE is first at the start. So let's get into it. PDEs, partial differential equations. Why? The big difference between these and normal differential equations are the fact that they're partial derivatives everywhere. So that means that whatever the dependent variable is here, so u, for example, here, it depends not just on t, but also on x. Okay? It depends on two different variables, two independent variables or more, and not just one. So, for this heat equation, right, that t and the x represent time and space. And you might think to yourself, well, why would we need to do that to talk about heat? And I want to kind of just do a little bit of a QC example for you. I don't know if you've ever had a cast iron pan before. If you don't have one, I highly recommend you get one because they're really awesome. You can start something in the pan, turn it over, stick it in the oven without doing anything special, and it turns out amazingly well. Clean up as a snap. Yeah, highly recommend a cast iron pan. And take a look. The thing is, it's heavy iron throughout the whole pan. So imagine that you have this thing and you're trying to model heat in it. Okay. If you put this pan on the stove, it's stone cold to start with. Here's the stove. I don't know about you, but my stove has open flame. I don't know. Anyway, sorry, I'm having fun. If you put this pan on the stove, that heat is going to be applied to the pan, and what's going to happen? Well, it's going to quickly warm up, right? But it's not going to warm up evenly. The how it warms up depends not only on how much time has gone by, but the location on the pan, right? At the initial time, I have an even temperature distribution at whatever the ambient air temperature might be. But once I turn the stove on, hey, the bottom of the pan is going to quickly warm up. So this is now warmer, and this is now warmer, and this is now warmer, and this is now warmer. And eventually, if you leave one of these things on the stove for a long time, that heat can eventually spread down the handle, and even down here it can get quite hot. But it's this eventual spread, right? For every point in space along the handle of this pan or the surface of this pan, right? For this point, at every given time, I get a temperature, right? So if this is on a scale between, say, 0 and 1, in terms of the x, the space, then, right, I could talk about this point as being tx equals, let's say 30, and looks like it's about 0.15. So what this says is that at location 0.15, what is the, at time 30 seconds, I can have a U of that describes the temperature at that point in time, at that point in space. And then as both T and X change, I get different temperatures. So I could talk about U of 300 at 0.15 to talk about what happens after 300 seconds have passed, or 5 minutes. I could talk about 300 and 0.25 if I was instead interested in what happens at this point. And you see, there's this sort of dependence on both time and space, and the function, the U, that fits an equation, one of these partial differential equations, that's the U that solves the problem, and it describes what the temperature is doing at all of those different times and at all of those different points in space. That's just one example, because there are lots and lots of different kinds of PDEs. There are PDEs that describe like the movement of stuff, and that's this transport equation. That if you have some sort of initial function, okay, some sort of initial data describing whatever U might be in terms of, so U could be all sorts of things, not just temperature, right? I saw a simple project in transport equation where it was pollution in a river. So at some initial time, there's a distribution of pollution in the river. Lots of pollution over here, not much pollution here. The river's clean, but over there, there's been a chemical spill, for heaven's sakes, and it's gross. And the river's flowing in one direction. So what that second equation does is it moves that stuff down the river. At every point in space, at every point in time, I can find the amount of pollution that's there, and that's described by whatever the function U is that fits that equation. So you can use these sorts of things for a lot of different simple applications. Simple because it's not simple, but also some kind of big heavy lifting things, right? There's the Navier-Stokes equations describing the motion of certain fluids, the Schrödinger equation, important in quantum mechanics, and so many others. You can look some up if you like, and some of them get pretty complicated. But as with every differential equation, the solution is going to be a function that satisfies left side equals right side. It just so happens that with PDEs, those solutions are multivariable functions. So for many applications, it's often useful to visualize a solution function in the form U of xt as a 1D function U of x that evolves as time moves forward, rather than a solution surface. Because you might think of U of xt as being a solution surface, but I can think of that cast iron pan and think of like an initial heat distribution, which is even, and then a heat distribution that changes over time. So for example, something like this, you might have that an initial distribution is like that, and then it gets hotter at the side, so maybe it looks something like, I don't know, like this. And at a later time, the heat is spread to the left, and the heat over the pan has grown to become like pretty even. So this is some sort of horrible set of 3 graphs. It's like an animation over time, where you can see that this progresses to this, progresses to this as time goes on. In general, I kind of wanted to do a little bit of a demonstration on what heat equation does, why it makes some sense, because a lot of people don't see this, and I think that it makes a lot of sense to me. So if you look at this top equation here, du dt equals alpha times the second derivative of u with respect to x. I want to just draw some stuff out to make it clear what this equation is saying and why it makes some sense. So let's do some special drawing here. So considering du dt equals it's alpha du dx, or alpha di squared u dx squared. I'll let alpha be 1 here just for the sake of simplicity, I guess. I'm going to put just the second derivative with respect to x here, a simple heat equation. Okay. I want to this is di squared u, dx squared. I wanted to do a little bit of a sort of the same sort of idea of what I did before, but talk a little bit about what's needed in these equations. And I want to do like a bit of a demonstration with animations that I kind of draw out. So actually, I might move this drawing down the page. Just give me 1 second here. Oops. Sorry, I just need to highlight and move this this chunk. Okay, excellent. That's what I wanted to do, because I want to describe this equation first. So the thing is, we know what these objects are, and I want to point them out because it's easy to look at these things and freeze up and freak out and think it's super complicated. But actually, what this says, du dt, going back to first year calculus, this is saying nothing more than the change in the temperature. The change in temperature with time. That's what this object says. Nothing more than that, okay? It's a derivative with respect to t, so it's the change in the temperature, the u, with the time t. That's nothing crazy. I want to now look at what's happening on the right-hand side. On the right-hand side, well, di squared u by dx squared. What if I have an x derivative? I have a spatial derivative, and I have a function u of x. I can view this. I can view the second derivative with respect to x as the concavity of that function, right? So this is, I want to say the concavity of the heat function as a function u of x. So disregarding the time dependence for a second, right? Disregarding the time dependence, it does play into things, okay? But I want to think about this for a second. If u is a function in terms of time and space, this here is the concavity of the function the function with respect to the x variable. So if I have some sort of heat distribution, at some initial time, maybe it looks like this. So I'm gonna write this down, and I want to describe what's going on here. So this is a heat distribution at some initial time. So imagine that this graph is like the snapshot of what the temperature profile is of some 1D, we'd say it's like a metal rod or something like that, okay? So at some initial time, t0, I'm taking a snapshot, and I have this function, a function that could be thought of as a function of just x, right? So it's like a u of x that happens to be at t equals t0. What I want to do is point out to what's happening here. What this equation says is that, oh, the rate of change in the temperature with time is equal to the concavity of the function at whatever point x we're talking about. So take a look at this. What this initial distribution is. Suppose we have like kind of hot in the middle, and then it kind of tapers down, so it's kind of cool on the outsides. Okay, what this equation describes is, oh look, kind of above this level, that's about an inflection point, agreed? Below that, it's concave up. Above that, it's concave down. Well, until I get to this other inflection point over here. So in here, the distribution is concave down, which means that this derivative is negative, and what that says is that the change in temperature and time is going to be negative. So that means that du dt is going to be negative based on this equation, and so I would expect that at that point, those areas between those two inflection points are going to be cooling down at that point in time. Okay? If I look over to this region and that region, these are concave up. And because they're concave up, this quantity right here is going to be positive, which means that du dt is positive. That means the change in temperature and time is positive. And that means that I would expect the heat to be increasing here and increasing there. So I'm going to just write here concave up, du dt is going to be positive. Okay, if we were not on the stove, right? If I just had a metal rod sitting on the ground and it was hot in the middle and cold on the outsides, what would you expect? You would expect the heat in the middle to start flowing to the outsides. Maybe the cool outsides get a little warmer over time while the hot iron in the middle cools down. That's what you're seeing there. And then you see what happens is that as time goes on, we get to a later t. So at some later t, t equals a little later, let's say. What's happened is the distribution in the middle will have come down, the distribution on the outsides will have come up, and I'll try to do this the best I can. You get something like this, where, interestingly, right, it's kind of evened out, and you would expect that to happen, right? If you were to leave that iron bar on the ground for a long, long time, what's going to happen? It's going to become an even temperature all the way across, right? The heat will have flowed from the places where it's hot to the places where it's not, and you get something that's a little bit more even. So you see at this later time, maybe the inflection point's now way over here, and way over, like here, and most of this part in the region is going down now, where only the little outsides are coming up, right? The second derivative might be much flatter now, so it might be cooling down at a slower rate as it comes to some sort of equilibrium. And that equilibrium happens at t equals a lot later. Really, as t goes to infinity. And then what you find is that it comes to some sort of average value all the way across, some sort of equilibrium temperature. So approaches an equilibrium temperature all the way across. So hopefully that's interesting. I wanted to show you kind of this demonstration because somebody showed me a demonstration like this once and it opened my eyes, right? It's one thing to look at this equation and just see a pile of derivatives, but those derivatives are actually describing physical properties that we can draw, we can feel, we can get kind of a hold of and maybe gain some understanding of. And this describes how heat transfer works in a really, I want to say intuitive way, because we know that that iron rod is going to cool down and reach equilibrium as time goes on. And that's exactly what this equation describes. So that's kind of like an introduction to the idea of what a PDE is. And we're going to kind of use this and go into a little bit of what it means to solve these things numerically. So let's try that out. Okay, so as I said, I keep talking about like an initial temperature distribution or something like that. I actually need an initial condition. And it's different than what you know from a normal differential equation if you have trading in that, right? So initial conditions describe the state of the solution when t equals some t0, but it's given as a function. I need an initial temperature distribution. I need a function that describes what that temperature is at all of the different points x. Oftentimes we, right, if I want a good problem for one of these, I'd like some sort of continuous function or some sort of function in any case that describes that initial state. Sometimes we don't have that. Sometimes in terms of numerical methods, sometimes for real life problems, we can only sample the cast iron pan at 20 different values of x going across. So I don't get a continuous distribution. I get a collection of data that I then need to use. So that's another reason why using numerical methods can be very helpful, because it's better at processing that data when that's all we have. So let's see here. For example, if u of xt represented, to get away from the heat example, the height of a skipping rope at location x at time t, u of x0 equals sine of x is an initial condition that might describe the skipping rope's height at the start at any point x in the domain. So right, maybe I have a skipping rope, and the height of that rope describes its initial state, that sort of thing. Okay, yeah, we need some other objects though, not just an initial condition. Oftentimes we need what are called boundary conditions. These can stipulate qualities of the solution of some sort. I've left it open because they can take a wide variety of forms at some points in the spatial domain. So in the above example, maybe the skipping rope is being held by a little kid at time t equals 0. If it's being held, that means that the endpoints are being fixed at a certain height. And so that might say that, okay, let's say u of 0 and t is fixed at a height of 0 to start with. And we describe the height up or down of the skipping rope as being the u, right? Something like that. So we need these initial conditions that take the form of functions now. We have these boundary conditions that could stipulate like different kinds of conditions. It could be a height, it could be a derivative, it could be all sorts of things at the spatial endpoints, possibly. And then we have to solve the PDE. And there are entire courses in this, right? There are entire courses in this. Some basic examples, like solving the heat equation, takes me a couple of whole classes to solve in an example when I'm teaching that topic. And that's not what this is about. This is supposed to be about solving numerically, and that's what we're here to do. So what I wanted to do for the last, 20 minutes or more is to kind of give you an idea for what these things are all about. But our job is going to be to use approximating techniques, using numerical methods in some sort of way. Okay, so let's kind of put this down in a mathematical form and then approach the problem using tools we already have as well as we can, okay? So we're going to talk about a first order PDE of the form du dt equals some function of these crazy quantities. So time, space, t and x, or they don't have to be time and space, they could be two spatial variables, but time and space are good to talk about. You might have f of u itself. So maybe you have a partial differential equation that itself depends, the du dt depends on whatever the value of u is, or even the derivative of the u with respect to space. To solve a PDE numerically means take the following steps. The first thing we need to do is to discretize. That was not spelled correctly. Let's try that again, Matt. There's a swing and a miss for you. I'm approximating the solution to this blank, and I left out the C. Discretize with a C the domain of interest. So that is, if we're interested in the solution on some interval I, so maybe this here is I right there, from here to there, maybe that describes the length of my cast iron pan or whatever, we consider only that interval at a finite number of nodes. So we're going to consider a bunch of nodes here from the first one to the last one. And there's going to be a finite number of them, and we can number them. X1, this could be X0, right? It might be X0 at one endpoint and Xn at the other with, X1, X2, and so on all the way through. And I get data at each of those nodes. So we kind of throw out the idea of working with a continuous function because it's hard to do numerically. Because there's an infinite number of points there to think of approximations for, and that might take us a long time to deal with. So a finite number of these nodes. The solution we find will be a collection of values at each of these nodes. So at x0, what's going to be happening at t0, t1, t2, t3, t4, t5? At x1, what's happening at time 0 and then time steps forward, t1, t2, t3, t4, t5? At x2, what happens at t0 and then t1, t2, 3, t, right through until the number of time steps that you want to take. And we're going to do this at every single one of the nodes until we get through to xn and we evolve that one forward in time. How do we do that? Well, our aim is to use an approach that's parallel to Euler's method. That's in the simplest case, okay? There are better schemes, more complicated yet, but we'll keep it simple for the basics here. And we're going to use an approach parallel to Euler's method to estimate the solution at a future time at each of the nodes. Because I want you to go back to that equation up here. And I want you to think of how close this thing looks to what the DEs that we did a couple of weeks ago, right? Those DEs look like this. du dt equals some function of t and u, right? We used y, so we could use a y here if you like. So compare. I'm just going to put this in a little bit of a cloud. But it's really similar, right? We had that the evolution in time was given by some function of t and y. We talked about this in terms of slopes of tangents and so on. The difference here is that, well, the du dt, it also depends on space and this thing here. So we're going to be playing kind of like an Euler game, except at every single one of those nodes, evolving each one forward in time. And because we need so many different pieces of information, it's better to think of it not in terms of a graph that goes forward, but more like an animation, you know, like something, it's this value now, and then if I walk forward on that tangent line, now it's at this value, so the value at x0 would jump from here to there at the next time step. And then if I use the tangent there that describes this crazy f of t, xu, and du dx, that's going to change it so that at the next time step, I'm up here, and so on. So I get like at every single node this is happening, and I'm playing, you know, n different or n plus 1 different Euler's methods at the same time, one at every point in space. That's different. That's crazy. It's complicated, but that's what we're going to do. Hopefully that makes a little bit of sense. It's pretty tough. And we have to start with something. We have to start with that initial condition. And you see why it's so important that we have an initial function. It's not good enough to have one piece of data, right? I need a piece of data at every single one of those nodes, i.e. I need some sort of distribution to begin with, some function that describes the initial state of you know, where the solution is going to start, and that's going to describe the initial temperature in the cast iron pan. It's going to describe the amount of pollution in the river, or whatever is being described by the PDE. Okay, so that way I've defined some u value at every single one of the nodes at t0, so I can start the evolution from some basis of some sort. Okay. Whew. Okay, at each node, sub into the PDE to obtain an approximation for du dt at each node. This tells us the instantaneous rate of change of u at each of the nodes. Compare Euler's method, we would take the f of t and y and sub in the current values of t and y to figure what the tangent slope is. How much should our estimate increase at the next time step? That's exactly the same thing that's happening here. At every single one of these nodes, I know what the x value is, so I have something to sub in here. I know what the time is because I'm currently on a particular time step, so I can figure out what this is. The u is going to be given by the initial condition because I'll have a certain height at every single one of those nodes, so I'll be able to sub in for that. And du dx, I actually have information about by considering, well, that's a spatial derivative. So I can actually use like difference approximations to determine what the derivative is at this node, right? And so on. And there are different sorts of ways to do that. But yeah, I can use different approximations using data between adjacent nodes to figure out what this thing is. And I can use all of that information, sub in for diut, and figure out what the tangent slope is to know how much the u value should increase or decrease at every single node. Okay, so it's an Euler's method style approach, and that's exactly what's going on here. We're using u at the current node at the next time step. Okay, so u at the current node and the at the current node and the next time step is equal to u at the current node and the previous time step plus h times, and then a function of, here's that f, of all of those different things with our data plugged in. So this is just the right hand side of the PDE with data plugged in. So you can see, right? I'm plugging in T0. I'm plugging in our current node. I'm plugging in the data at that current node at that current time. And then here's that derivative of the stuff. I'm just taking all of this information, I'm putting it into the f, whatever the f might be, and we're going to proceed from there. And as I said, we can use finite differences to approximate this diu/dix quantity at each node as we go forward, if necessary, if that quantity does appear. And then you repeat that process again to advance the solution approximation forward in time. That's how it works. It's pretty ugly, but we're going to actually do a simple example, and I'll show you how a little bit of it works, and then do a demonstration, and it's really pretty cool. So this is the transport equation. This is what I said was that equation that models, like, you know, the pollution flowing down the river, but really anything flowing in a river. It can model like traffic problems. So if you have a highway and you have cars, traffic moving at a particular speed, that's a constant. This is something that can model that as well. We're going to use initial data of u of x and 0 is sine x. So that's saying that at the start, we have a sinusoidal sort of distribution, and we're going to evolve things from there. What this equation should do is move that sine of x kind of down the river, if you will. We're going to institute a boundary condition at one end, u of 0t equals 0. So essentially this is saying that at one of the spatial endpoints, the data is always going to be equal to 0. And so we're going to look at a solution to this thing on the interval x from 0 to 3, and we'll use a domain partition size of delta x equals 3/50ths. That sounds really weird, but really it's just taking this 3 and dividing it into 50. So that we're going to have 50 different intervals, like sub-intervals between the two, and 51 nodes overall, because we have the one on the far left, and then the 50 different intervals, and then the one on the far right. So this would create, this creates 50 sub-intervals and 51 nodes. Okay, so we have basically x0 through x50, or maybe you want to say x1 to x51 if you're stuck in MATLAB and your arrays start at 1 for reasons that you just don't understand. But we have 51 nodes in total, and we're going to discretize the domain. See, that's what I did. I did x1 and x51 because I think that's what MATLAB does. And the other nodes are evenly spaced through that domain. You don't have to do an even spacing, but it's a heck of a lot easier to program. So let's work with this. First, we isolate for diut. This is to get the PDE into the right form, because really I need to get it into that sort of the same sort of form that we can have like diut, so how it's going to evolve with time, dependent on stuff. I need that form so I know how to evolve it at. And so that's the importance of that. Luckily, this equation is pretty simple. So this is du t equals negative 0.8 du x. Okay, we talked about this thing and how it's complicated, right? If all I have is a finite collection of data points, how do I know what du x is? We don't know what that is. We have to estimate it. That's what I was talking about before. So we have to estimate this quantity using finite differences. And we talked about that stuff a few weeks ago. In fact, you did a test on it, and you rocked it. So that's the thing, right? I need to replace that du x by some sort of difference approximation. So get ready for this. It's going to be pretty ugly here. But du t is going to be approximately minus 0.8. And then I need to change du x into some sort of finite difference approximation. And that's going to be, well, I wrote it down here so that I didn't screw it up, because there's a lot of like indexes and stuff like that. But we're talking about at the node xi, if I were to use a centered difference approximation, because we know that that's generally a nice approach where the error shrinks quicker as the step size decreases, I'm going to go forward a step. Forward a step. And I guess we're at time 0. So I'm going to say 0 to begin with. Minus, oh, for heaven's sakes. There we go. Sorry about that. My page skipped on me. Minus backward a step. So xi minus 1, 0. Over the difference between the two, right? xi plus 1 minus xi minus 1, like that. Okay, and that means that if I want to know how much things evolve over time, this quantity is my f. This is the f in our scheme. And really it's this here. So this is just an approximation of the f. And this is approximating that derivative in this sort of way. And I can evolve forward in time by taking my old u and adding some sort of step size in time, h, times that quantity that we just identified. So u of xi and 0 plus h times that quantity, minus 0.8, and then, let's do it. U of xi plus 1, 0, minus u xi minus 1, 0, all over xi plus 1 minus xi minus 1. Like this. Close bracket, and this is how the scheme is going to work. That's going to update u at the node xi, but I have to do this same thing at every single one of the interior nodes. And it's using data from the node in front of it and the node behind it to estimate the derivative. And it's going to evolve forward by that quantity h. And I didn't describe the h, but h is going to be some small step in time. Maybe it's like 0.01 or something like that. And this updates all of the different values of u, so I figure out what the best estimates would be at the next time step. That's going to create a new function, and we would use that as the new data to help continue the process. Okay, some small considerations. This is great for all of the interior nodes, but at the right endpoint and at the left endpoint, you don't have enough data to use a centered difference approximation, right? In the interior, you're going to have nodes on either side, and I can use information from in front and information from behind to estimate the derivative. But if you're the first one or the last one, you don't have either a front or behind. You're missing one of them. So at those points, you have to use either a forward or a backward difference approximation. in this example in particular, at the right endpoint, we use a backward difference approximation, which should make some sense. At the left endpoint, remember that we had a boundary condition where we were designating that it was always held to 0. So we don't need to use a difference approximation at all because of that boundary condition. Instead, we can just set the left endpoints equal to 0 all the time. And yeah, so then you kind of throw that in. I've got a program set up. I'm going to share it with you with some code, but I'm actually going to run it right here so you can see what's happening. So let's see if this works. Maybe just my luck for it not to. But take a look. You can see here that the solution is slowly moving from one side to the other. The shape of the curve is preserved. I'm taking small time steps to make sure that I'm getting a reasonably accurate solution, but there will be some error that accumulates here due to the nature of things related to Euler's method and the error associated with that. And the same sorts of errors occur here. So thought you might think that was interesting. Maybe we can look at that again. I've got an animation here. This is through MATLAB actually. And it's not too hard to look up how to do animated plots, but they're kind of finicky to do. So, but it's neat. You can see that sine curve evolving forward in time. Imagine this is like pollution in a river or whatever. It's just moving along with the river. And it's described by this numerical solution. So pretty cool stuff, I think. And I recognize that there are a lot of moving parts here. No pun intended. That it's a complicated setup, but I think there are enough pieces here that it can make some sense. Okay, some last considerations I want to talk about here before I just quickly show off the code. There are usually some conditions imposed on how small the time step h must be to properly capture solution behavior. If you take too big of time steps, right? If your h is too large, it's the same sort of deal with Euler's method. If you take huge time steps there's no way in 1,000 years that your solutions are going to be anywhere close to the actual solutions, right? Your numerical solutions are going to be far, far off most of the time. The same thing happens here, except also at every single node, you're going to see that error accumulate quickly. You need to make sure that that particular conditions are fulfilled to get reasonable approximations for these things. And a common condition that's used is this CFL condition. Courant, Frederick, Louis. Nobody ever says those names or even usually knows that. People just say CFL conditions, and there are certain criteria for what those are. And there is a particular condition on the example we just did that I made sure was satisfied when I put together that code. What I just did and covered, and it looked really gross, that is the very, very basic scheme, and it's full of error and full of awful, and you'd never use this. But it's good to convey the concepts, right? The idea that you have a collection of data that evolves at a time step, that uses, methods that are sort of familiar, that are related to what you know from Euler's method. But as a matter of fact, you can extend this and instead do things that are more akin to multi-step methods at each point. So forget Euler, do some sort of Runge-Kutta scheme at every single one of those nodes, and you can see how this inflates to become like a big deal. There are a couple still things that I want to talk about. You can have PDEs that involve second derivatives, and so you could just use different kinds of difference approximations. We did talk about a difference approximation for a second derivative back when we did those notes, and you could use that here too. There are other kinds of boundary conditions. I kind of mentioned this before. You could stipulate that instead of at one side there, the data has to have a particular height, you could say that it has to have a particular slope. And then try to capture that in various ways. You could stipulate, for example, that at one end of the spatial domain, the slope has to be 0. And if the slope has to be 0, maybe the best way to stipulate that is to actually say that whatever u0 is, u1 has to be the same height to make sure that I get that kind of horizontal behavior at the end. there are different kinds of ways you can implement conditions of different kinds that might be useful. It's a very deep topic. There are entire courses in this. There's so much more to learn, and I just want you to get the basic understanding of what's going on with PDEs and what's happening with these numerical schemes. So I want you to do nothing more than to take the code that is here at the end and play with it a little bit, right? I'm not going to test you very deeply on this. I just think it's important for you to have that basic understanding. And even though it's complicated, right, I want to point out the fact that entire animated plot, so like running what I ran, defining the initial conditions, there's even a couple of white space and comment lines here, and producing an animated plot still only fits in 41 lines of code. It's not actually that big of a deal code-wise. And I'll leave it to you to kind of work through what's happening here. But you can see there are a bunch of arrays that are being updated, and it's a cool little piece of code to play with. So have fun with that. Yeah, I think I'm going to leave it there. This is it. I wanted to kind of fit this into one lecture. I'm sorry it's gone very, very long here, but I don't want to make this like a multi-lecture sort of topic because of the fact that I know that I'm not going to test very deeply on it in the final exam. And I want this to kind of be like a one-stop shop of like, hey, you need something for PDEs? Come back and watch the basics here, right? You can do better. There are more complicated schemes, but we talked about the basics of PDEs, and I hope that the demonstrations with the cast iron pan or whatever, like that was helpful for you to kind of visualize what's happening with those equations. And then hopefully the scheme kind of made some sense at the end, but let me know. All right. I guess we'll leave it there. I'll say adios to you all. And we're going to change gears again and talk about a pretty cool topic next before launching into a discussion of numerical integration. So stay tuned. There's more to come, and I look forward to it. Bye for now.